I think the mic is on one of those computers.
No, the mic is overhead, so.
Oh,
we
it's
can
overhead,
hear it.
okay, good. Good job. Good.
All right, hi, I'm Jade Boysen. My pronouns are she, her, hers, and I'm from Augsburg University. I work with Jeff Walter, and I also worked in the Layton lab at the University of Minnesota with Weyl semimetal behavior in shandite, Co3Sn2S2, single crystals, and thin films. An overarching goal of the Walter Research Group is to use sulfides, and one of the applications that we are working towards is new electronics. So we're really big on sustainability, and something that we can do sustainability wise is look at the elements that we would use in these electronics. We're looking for elements that are low cost, environmentally responsible, super abundant. As you can see in this picture, there is a ton of waste product of sulfur at oil refinement processes. So we know that sulfur is a great material to use and can check all of these boxes that we want for sustainability. But sulfur by itself doesn't really do anything too interesting. So how can we add a little bit of functionality? Well, it turns out that we really want to see the magnetic properties that we can use for electronics. So adding sulfur with transition metals like iron, cobalt, and nickel can show kind of these interesting magnetic properties. And if you look on this image of abundance versus atomic number, you can see that all of these elements are pretty abundant and not going to go away super fast. So using them is another great quality of that sustainability aspect. And one of the sulfides that we are interested in is this shandite. It has a quasi 2D structure. If you look at this image, the red cobalt atoms are stacked in their own planes in a hexagonal lattice, making it unique. It is also a metallic ferromagnet with a Curie temperature of 175 Kelvin. And another cool property it withholds is that it is a Weyl semimetal. So what is a Weyl semimetal? Well, it holds a unique band structure that is topologically non-trivial. The cool thing about band structures in topological things are super exciting. If we look at this image below on the bottom here, this is actually for a topological insulator, but most normal materials that you see will have kind of like this parabolic look to them in their band structure. And for a topological insulator, they start to become more linear, and you get this like over play of your band structures. And so the cool thing about a topological insulator is that on those surface states, you have those bands that are overlapping. But with a Weyl semimetal, instead of just happening on the surface, it starts to happen in the bulk. So you're getting it in the whole material instead of just on the surface, which allows for electrons to be more mobile and free moving, which is the property that we're looking at because we're super interested in that band structure along with magnetism. And another thing that comes with Weyl semimetals is this giant anomalous Hall effect. And so a little bit on this Hall effect. An ordinary Hall effect, when we measure a Hall effect, we take that material here in purple and we run a current through it. And then we apply a magnetic field and measure a Hall voltage transverse to that current that we're sending through it. And when we would get an output of magnetic field versus Hall signal for our ordinary material, you would see that it was like linear because you would just have the magnetic field that we're applying. But the cool thing with our material is that it is a ferromagnet. So it has its own magnetic field as well. So we have the magnetic field of the material as well as the one that we're applying. So instead of seeing just like a linear line in our graph in our magnetic field versus Hall signal, we actually get this cool hysteresis loop. So when we scan our magnetic field, you'll actually see the two lines coming from the one we're applying and the sample itself. And when it comes to this cobalt shandite, it is super big compared to other ferromagnets. So you can kind of see the scale that the other ferromagnets are on, and our material is all the way up here. So that is a cool thing that we are trying to find as well. My goal was to grow high quality shandite in order to study these properties in a little bit more detail. It hasn't really been done a whole lot, and so we want to make sure that we have samples that actually are the material before getting further into this Hall effect measurement. And so we do have to grow the samples first. We have two methods. We have a single crystal method and a thin film method. So more of a fundamental, like breaking down and the bulk method. So I'm going to start off with our thin film method. So we start with a substrate and then we sputter a metallic film on it. Usually it's cobalt-3 tin 2. And then we throw that little film into a quartz ampule with a little bit of tin sulfide. And then we heat it to a sulfidation temperature. And so we did this with multiple temperatures, and we wanted to see what our samples looked like, because a big thing with films is that we want our films to be homogeneous and super smooth. So if you take a look at my images, they're all in 1 micron. And as our sulfidation temperature starts at 450, we can see that there are big, large chunks that are just chilling outside or on top of all of these like mini grains. And so as we heated the sample, we saw that the grains started to get a little bit more uniform and smooth over the entire surface. And then as we hit 575, we see exactly what we want to see, with all of our grains being the same size. And then as we increase the temperature more, we want to just see what the effects were. We did get a good film, but we wanted to increase even more. And as you can see, those larger grains start to come back. And there's also a couple of holes that start to form within our samples. So we do have a nice look at our film, but we don't know if the film is actually made up of what we want it to be made up of. And so we took these images and we did EDS on them, which is energy dispersive spectroscopy, in order to find out if the material within the film was actually what we wanted it to be. So our target was 3 to 2 to 2. And so we set our tin to 2 and then created our ratios from there. And you can see in the 450 that we're slightly higher with the other two values than we would like to be. And so as we increased temperature, shoot, the bar is in the way, but this one is 3.4 to 2 to 2.5. So getting closer to the ratio that we want. And then this sample is our closest to the 3 to 2 to 2, which is good for us because now we know that that material is in this nice looking film that we want to use more of. And then as we get even hotter, you can see that our ratio actually gets worse again. So not exactly what we want, but even though we have all of the right things, we do care about the crystal structure. So we actually performed some X-ray diffraction on these samples. And so if you look at our intensity versus 2 theta, this is our raw data on the top in black. And then the fingerprints for other materials are listed underneath. And so when the peaks line up, you can tell that that is in our sample. So the blue peaks line up, but there's also multiple peaks that don't line up with that shandite structure that we want. So we know there are other materials within it, which is why there are a couple more listed below to fill in those peaks that weren't identified in that shandite fingerprint. And then as we get hotter, we see that those impurities start to go away and we have purely shandite, which is exactly what we wanted. And then if we heat back up, some of those impurities start to come back. And so we see that we've optimized grow film at 575. And now that we've done that, we want to grow more of them so that we can do magnetometry and transport. That's all for my thin films. So I'm going to shift to my single crystals. We use chemical vapor transport to make our single crystals. We load a reactant powder with a transport on one side of a quartz tube, and then we seal it. And we put it in a gradient furnace with a hot zone and a cold zone. We vaporize our reactant powders, and then they would travel and cool and recondense as single crystals in the other side. But this process is like super long, takes about 3 weeks. So it's not generally an easy process to go with. And since our material is so new, we actually have to make a precursor powder. So that also takes around 6 days. So pretty lengthy process. But if you do it right, you end up with great results. But we would stick all of our stoichiometric amounts in there, heat it, and get one solid powder of just our cobalt-3 tin 2 sulfur 2. And so we did X-ray diffraction on these as well. And we did a study of adding extra sulfur because sometimes when you heat sulfur, it'll stay in the vapor phase and not go in and recondense. So we did a study just to make sure that we had the right sulfur content. As you can see with 0 excess sulfur, we have exactly the reference pattern lines up with our peaks, which is great. There was a couple that we couldn't identify. So it's nearly phase pure, which for us is good enough. And if you add extra sulfur, you can see that it kind of kills the growth and you have so many other materials within that sample. So we're using the one with 0 sulfur. And we actually did get a single crystal. As you can see, they're pretty small and super fragile. So we stick them in the furnace for 3 weeks and we can't look at them. So we don't know if we actually have crystals until the process is over. So this was a big treat to get at the end of that 3 weeks. And then since we did get a crystal, we were able to do some electronic transport. As you can see here, if we cool our sample, our resistivity goes down. That's showing us that the material is a metal, which is exactly what we want. There also is a tiny kink in the graph at about 175 Kelvin. And if you remember back from my previous slide, that is the Curie temperature for the material that we were trying to grow. And then at 110 Kelvin, we get that beautiful hysteresis loop that we would also associate with being a Weyl semimetal when we look at our magnetic versus our Hall measurement. And then we can take that Hall signal and calculate a Hall angle. And when we compare that Hall angle with the other data, we see that our sample is just like the other one. We get that giant anomalous Hall effect from our sample. It's not perfectly where previous studies have shown, but it is off the curve, which is exactly what we wanted to see. So it gives us some hope for the future. We're really focused on the interplay between magnetism and that band structure. And so getting an optimized growth at 575 is really exciting for our thin films, and our single crystals are growing and we're getting them. So it's exciting moving forward to get those measurements for magnetometry. And thank you for your attention. I'm willing to take any questions.
All right, we're running up against time, but we got time, maybe time for 1 or 2 questions. Yeah, go ahead.
So you mentioned, right, that, you know, these this material, this shandite, has this anomalous Hall effect. Is that based really on that one previous measurement? Because you also said that it was really hard to actually make. I mean, you described how it's hard for, right? So you've got one previous measurement by some other group observing this, and then your work, is that, or was it theory that predicted the anomalous Hall effect?
Yeah, it's just the one measurement that we saw in the previous literature that we started this material from. There was previous research done on it being a Weyl semi-metal, but no one to really back that until that paper.
One more question. then we'll-
Sure. What's the potential use for this? I'll just say in industry.
Yeah, so using it in electronics, it's a sustainable one. So the cost and having it long term is better off than what we're using right now. But we haven't been able to get it to perform at like room temperature. So that's the goal of our research, is to kind of figure out how we can sustain that ferromagnetism at room temperature for it to even be applicable in electronics today.
Okay, thank you so much. Remember to fill out a survey for you, the students. You should have a session 4 ballot to vote for the best poster. Do you want to post the link to the online version for Zoom? You got it. Okay, so you should have that in the chat if you're on Zoom. And I'll ask James, maybe tell us where we're going next real quick.
Sure, so the next thing, and you can actually stay here if you just want to watch this stream, but I might do that, is keynote talk. It will start just in a couple minutes in the main room, and there's plenty of space down there if you want to go and see the presenter in person in the front of the room. But I think I will just probably stream it up on this screen if you want to just stay here and watch it on Zoom. And then, of course, the Zoom participants will be doing exactly the same thing. So thank you again for attending this session. After the keynote, there will be another pair of riveted talks, some down there, some down here, followed by more exhibit.
Right, and it's a lunch session, right?
Well,
Bring
it's a
your
quote lunch session. We're not taking a lunch break, but if you have a lunch, then that would be the time to eat it, would be during that session. Let's try to stay apart.
And what's
your
your
recording?
When does the keynote start?
12:05.
12:05, so in 3 minutes.